In 13.8, we'll be discussing continuity and the mean value theorem. These are two separate topics. And then I'm also going to show you a new function called the greatest integer function. So we're going to start first with continuity and its definition, which comes in three parts. And it starts like this. A function is continuous at x equals c if the following conditions are met. Okay, so first thing is that f of c exists. This is to say that for a function, so let's draw parabola here. So point on the curve when x is 2, f of 2 exists. There's a point there. We'll say that that's 1, so we check it off the list. F of c exists. Step 2 is that the limit of f of x as x approaches c exists. All right, so let's say as we approach 2, coming in from each side, we've got from the left side, we're approaching a height of 1. From the right side, we're approaching a height of 1. So the limit does exist. So remember that for the limit to exist, because the limit as we approach 2 from the left of the function is equal to the limit as we approach 2 from the right side of the function. And that's what's happening here. So the limit exists. The third thing is that the limit of the function as x approaches c must equal f of c. In other words, numbers 1 and 2 must be the same value. And you can see that here. We had the limit is 1, so that's what we came up with here. The function's value is 1. These two things are the same thing, and that's the third condition being met. The limit is equal to the function's value itself. All right, so this is a continuous function at 2. So let's go on to an example of how we might use this definition of continuity in a problem. So we're being asked to find the values of a and b that will make the given function f continuous. So f of x is given as a piecewise function. We're going to start with 2x minus a when x is less than negative 3, ax plus 2b when x is between negative 3 and 3, and b minus 5x when x is greater than 3. So to make a function continuous, what we'd like to have happen is when we reach values like negative 3, we switch from one function to a different piece of the function. When their x values meet, when they're the same, for the function to be continuous, their y values have to be the same. And so this means when x equals negative 3, 2x minus a must equal ax plus 2b. So we plug in negative 3 for x, And then we'll simplify this. And you'll notice we can simplify it a little bit more. I'm going to divide everywhere by a -2. And that just makes for a really nice simplified equation. So not much we can do with one equation and two unknowns. So we're going to repeat this process. When x is 3, we have the middle function and the bottom function. When they have the same x value 3, they must have the same y value. So that's to say when I plug in 3 for x, the functions must be equal. So let's plug in 3 for x. We get 3a plus 2b equals b minus 15. We'll get our like terms together. And that's as simplified as we can make that one there. So now what we do, we have a system of equations. The values of a and b are the same for all parts of this problem. And so this means from our system, we get to put these two equations together, and we need to solve for a and b. So you can either use substitution method, or I can just line up the bottom one here. 3 is equal to a minus b. And I can just use my addition or elimination method. So we're going to add these up. We get 4a is equal to -12. So a is -3. So there's the value of a. You substitute that back into either of the original two equations, and we'll solve for b. So let's go here. 3 is equal to -3 minus b. So 6 equals -b, and b is equal to -6. And that's our answer. In part 2, we're going to discuss a new function called the greatest integer function. It's also known as the step function because of what it resembles. So that function has some notation that looks like this, kind of a double bracket. And the definition here of the greatest integer function, so what this is, okay, it's the f is the greatest integer, the largest integer, less than or equal to x. So what's important to know is that my domain is anything. I can plug in everything I want to. Domain is all reals. And for now, we're just going to say the range is just an integer or integers. And so we'll write that out once we get going in our picture here. So we're going to do two things. We're going to make a table here of values to kind of help walk us through our graph. And then I'm going to make a graph over here for our picture. So we'll talk about x, and then we'll talk about f of x. So I'm going to start with something like 0. So if I plug in 0, what is the biggest whole number, integer, less than or equal to 0? Well, that would be 0. 0 is equal to 0 itself, and that's an integer. When I plug in something like 0.1, 0.1 is not an integer, so f of x cannot be 0.1. F has to be the biggest whole number less than 0.1, and that would be 0 again. When I plug in 0.2, 0, 0.3, 0, 0.9, 0. It's only when I get to 1 that I finally get out 1, since 1 is equal to itself, and the output has to be an integer. When I plug in 1.1, I get out 1. I can't get 1.1 as an answer for f because 1.1 is not an integer. I need an output, a whole number that is less than 1.1. So the nearest whole number less than 1.1 is 1. When I plug in 1.2, I get 1. 1.5, I get 1, and so on until I get to 2 when it finally spits out 2. And this pattern continues. Okay. It also continues with the negative numbers. So let's go into the negatives. If we plug in negative 0.1, we want to go to the nearest whole number less than negative 0.1 would be negative 1. And we would get this out. Negative 1, until we got to the other side. Once we get to negative 1.2, we're going down to negative 2 because we want to get a whole number out that's less than itself. And so this just keeps on going, this big list. And so let's start making a graph out of this. So plugging in, and I'm going to use a different color so this shows up a little bit better. 0, 0, 0.10, 0.20, 0.30, all the way until I get to 0.9. Okay, so all these values here. And when I finally get to 1, which would be right here next to it, when I finally get to 1, I get an output of 1. And this happens all the way until I get to 2. Okay, so we're going to get an output of 1 until we get to 2. And at 2, I get out 2. So right here. And this will go on until we get to 3, at which point I would get out 3. And so on. But this isn't good enough though. So to show that we get infinitely closer and closer to these values, but at 1, 1, 2, 2, 3, 3. So to show that, we're actually going to show that underneath, you have these open values here. That way we can see that our functions don't overlap, right? And that would be bad. Then it wouldn't be a function. So we don't have that overlap there, that space between. And you can see it does start to look like a set of stairs or steps. And that's where it gets its name from, the step function. So let's work back here with our negative 1 values. And then negative 2. And negative 3. And this just keeps going. All right. So that is the greatest integer function, and we talked about its domain. If you look left to right, it does contain all x values. We were able to plug in everything that we wanted. Notice the output, the range here, is just the set of integers. So we're going to write that down. Or we can write that as y is an element of the set of integers. Hopefully you remember me talking about that double bar z in class a while back. Before we move on, we're going to talk about, or just do a little bit of a limit review here. So we've gone through the domain and the range. So now let's call this problem number 2. We're going to do the limit of our new function here as x approaches 0 from the left side. So x equals 0 here at the origin. If we come in from the left side, we're actually down here on this step whose height is negative 1. And it just stays there. It's just a nice height of negative 1. But what about the limit of this function as x approaches 0 from the right? So at 0 here at the origin, we're coming in from the right side of 0. We're on the step that's a little bit higher. Actually, it's at a height of 0. And so this, of course, leads into what is the limit of the function as x approaches 0. So not approaching from either side. And remember, in the definition of continuity, we reviewed how do we know when the limit exists. A limit exists when the left and right hand limits agree. And in this case, they don't agree. They disagree. So this limit here does not exist. Okay. The last thing we're going to do is talk about sketching a translation of the greatest integer function. So let's say that we wanted to sketch, let's do number 3, sketch y equals f of x plus 1 plus 2. So like any other function, this is telling us to take our greatest integer function and to translate it 1 unit left and 2 units up. I'm going to take out my little f there. We don't want that. So 1 unit to the left and then 2 units up. And what I like to do is just take that first step at 0, 0. That's 1 unit in length almost. We're going to translate this point here at 0, 0. 1 unit to the left, that would be -1, and then 2 units up. Okay, so it would end up right here. It would be 1 unit in length. It would be open on the other end. And from there, we just have all of our steps behind it and in front of it as well. So up 1, length of 1, up 1, length of 1 unit, up 1, length 1 unit. And you just keep going that way with your stairs. In the last section, we'll cover the intermediate value theorem. And I already have it written out here for you, and I'm going to add on to the picture as we go through it. It says if f is a continuous function on the closed interval a, b. So first, I'm going to pick out a and b. So I'm going to put a, I think, right about here, and b, let's see a good spot for b. I'm going to put b about here. Really, they could go anywhere. So this whole function is nice and continuous everywhere, so you could pick a and b to be anywhere. And then it says k is any value between f of a and f of b. Okay, so here's what happens. We have a, and then we have point on the function. This is f of a here. B goes up to our function also. I don't think this is probably where I wanted it to be. We're going to move it. We're going to move A. I want it to be a little bit lower. It gives us more options. Okay, so let's put A over here. So this is going to be f of A. And then B, we get all the way back over here. This is f of B. See, so that's a lot nicer. A little more space in between. Now K is between them. So let's find a good spot for K. Can be anywhere in between them. Between meaning not on, so we can't pick f of A or f of B, but you can pick any space in between. So let's go right here. So we'll choose this spot for K. All right, so it says there has to be at least one C in the open interval AB. So this means C is an X value that is in the interval AB. X value within the interval AB. That's what we're looking for. So it says there has to be at least one time C where f of c equals k. So this means if I plug c into my function, k is the output. So it's a coordinate pair, isn't it? It's saying c, comma, k. Okay, so I have k, a height, a y value. So let's see where k takes us over here on our function. So I've got this point here, which is not, this would have a c value, its x value would be here. And this point is not in between a and b. So let's take that further over this way. And we have a point here. And there you go. that value is between a and b, which is good. And you can see that there's another time where my function has this height over here, this x value also not between a and b. So what the theorem does is it guarantees us that there's at least one time where this will happen. There's at least one time, one point here where the value is between a and b that you will get this height. That's what we're looking for. It does say at least, which means it potentially could happen more than once, twice, 3 times, depending on how big our interval was. If we had made A much farther away, we probably would have had a lot more results. So what this theorem does in context of problems we'll be working on is it just says, basically, if you have a continuous function, you have this nice connected, no breaks, nice smooth turns. If you have this nice continuous function, to get from one point to another, you have to pass through all the points in between. All right, and that sounds obvious, but I'm going to show you what that looks like in the form of our example here. So I think we're on example 4 now. In this one, we're going to let f of x be the function x squared minus 2. And we're going to do several different things with this. So for part A, let's see. It says show, or another word for prove, meaning we're going to use the theorem to do this. Show that there must be a time when f of x equals 7 on -1, 5. And we have to do this using the intermediate value theorem. Okay, so notice my theorem tells me exactly what to do. It's almost like a checklist of things. The first thing it says is that f has to be a continuous function for this to work. So step 1, we want to write out f is continuous. If it's not continuous on the interval they're using, which f is continuous everywhere, but specifically it is continuous on -1, 5, then the intermediate value theorem doesn't apply. If it's not continuous, you just throw it out. You would say the IVT doesn't apply. So the second thing is we have to show k is between f of a and f of b. All right, so our value of k is right here. Remember, our formula says f of c equals k. So this is the f of c equals k part. So k is 7. So we're trying to show that 7 is between f of a and f of b. Remember that a is -1 and b is 5. So again, we want to show 7 is between f of -1 and f of 5. So step 2, show 7 is between f of -1 and f of 5. Okay, so here's what you do. You find f of -1 and f of 5. So f of -1, if we plug -1 into our function, we get -1 squared minus 2. And 1 minus 2 is -1. F of 5, we get 5 squared minus 2. 25 minus 2 is 23. And you would agree 7 is between -1 and 23. Yes. So now, because we've found all those things out, the intermediate value theorem tells us that there must be a time when our function equals 7 on our interval. So the third thing you're going to do is write out your proof or conclusion here. And that's going to look like this. We start with, since f is continuous on -1, 5, and 7 is between f of -1 and f of 5. So I'm going to write that this way. It's important that this step is not just something that you claim, but that you have the work here to support it. So this is part of the problem. You actually do have to show this before you write out your conclusion here. So since f is continuous and 7 is between f of -1 and f of 5, then, and all you have to do for the rest of it is just rewrite the intermediate value theorem that says there is at least one C in the open interval, what is it, -1, 5, such that f of C is equal to 7, not K, 7. You want to apply it to this problem. So there's like 2 changes here of how you'll write it at the end. All right. If you feel more comfortable using some different wording than just copying down what the intermediate value theorem says, that's fine. But I find it reassuring and I like to just do that. So that was part A. You want to make sure the function's continuous on the interval. If it's not, the intermediate value theorem doesn't apply. You state that and you move on. Step 2, you actually have to find f of A and f of B. And step 3, you write out your conclusion. Okay. So in part B of this problem, so we've done our little proof now. In part B, we want to find this value of C. All right, find when the function f of C equals 7. So that's just this little end piece we just did right here. F of something equals 7. So we're just setting our function equal to 7. Our function x squared minus 2 is equal to 7. And so we get x squared is equal to 9, and x equals plus and minus 3. Now, it's important to remember that this value of C is between -1 and 5. So we can only pick values between -1 and 5, which means that we will throw out -3, and C is only the value 3.